Okay, I have finished command filter. So from today onwards, I will teach model predictive control. Now, in the industry, the most common controller is PID. The next most common controller would be model predictive control. Okay, so PID is the most basic one. If you want something more advanced, then it will be model predictive control. Okay, so that means that, so to speak, if you do a master's or PhD in control, you cannot go to the industry and say you don't know model predictive control. All right, is just like if you graduate and you work in control, you cannot say you don't know PID control. It's just like the medical doctor say, I don't know Panadol. All right, is that this is the most basic control. At least model predictive control is the second most common controller in the industry. Okay, so now I will teach model predictive control using state space. Now, we start with the preliminaries. All right, assume that your process is given by this state space model. All right, your plan. Now, it is standard in state space that in most control, we know that we need to put in integral action. If not, there will be steady state error. So in state space, the standard way to put in integral action is to get an augmented plan. All right, augment it with an integrator. So how it is done, it is like that. All right, and I will in my course, I will only deal with single input and single output plan. Okay. So in other words, Y is scalar. This is output, single output, so it's scalar. Single input, UK is also scalar. A, B, C can be vectors. All right, or matrices. Now, take note later on, there will be more complication. U is the real power received by the plant. So if your plant is a heater, U will be the real watts. All right, how many watts sent to the plant, or the voltage really sent to the plant. This is the real power sent to the plant. Now, in order to put in an integral control, the model predictive control will calculate delta U. All right, so you make a distinction. When you see delta U, that is the power calculated by the model predictive control. So he will calculate delta U by the model predictive control algorithm. After that, we will then use this equation to get the real power UK, which is here, and send to the plant. All right, so you must differentiate between what is calculated, delta U, and what is the real power sent to the plant. So by doing this action, then what really happens is that U is the integral of delta U. Okay, how do you see this? I give a very simple example. Integral action or integrator or integral control, it is really has to do with integration. That's why we call it integral control, integrator, whatever it is, has to do with integration. Now, in secondary school, when you integrate, we always x-axis and y-axis, we always like that. All right, then there's always a curve. Then when we learn integration, then in secondary school, we always have this one. Okay, this is x1, this is x2. And then what is the meaning of integration? So we will integrate, we always do the standard thing is like that. Then x1 to x2. We do this operation in secondary school, then we get a number, let's say 3.4. What is the meaning of this number? The meaning of this number is the area under the curve. So integration in secondary school, we know integration is to find area under the curve. Now we go through a very simple example to show that this equation here basically is integration. In other words, U is the area under the delta U curve. So U is an area. So this is integration. How you see that? Let's just go through a simple example so that you have no doubt in your mind that there is integration going on. All right, so if I assume that, let's say we have this. So this is K. So I start from -1, so to 0, to 1, to 2, to 3, to 4. So if I have a delta U that is, okay, I also will have 1, 2, 3, 4, 5. So I have a 0, 1, 2, 3, 4, 5. My delta U curve, let's say, is like that. Okay, so this is my delta U curve. You see what is my U curve according to the equation. So when it is here, it is at when K is at 0. So this is 0. All right. This, when we start, this is also 0. So U will be equals to 0. So from here to here, everything is 0. So my U curve from here to here is like that. Then after that, at the next interval, this is 1. The previous U is 0. So at the interval 1, this must be 1 because it's 0 plus 1. So this is 1. So at this interval, it will be 1. So my U curve will be 1. Then at the next interval, which is here, my delta U is 2. So I have a 2 here. My previous U, which is this one, is 1. So my new U curve must be 2 plus 1 equals to 3. So you see that this interval must be 3. All right. Then at this interval, my delta U curve is 1. So this is 1. What's my previous U curve? It is 3. So my new U curve must be 3 plus 1 equals to 4. So my U curve here must be equals to 4. So this is my U curve. Then you can convince yourself and see, oh, what is the area under the delta U curve? You see, this is 1, this is 1, this is 1, this is 1, this is 1. So this whole area will be 4, which is, you see, up to here is 4, and this is 4. So simple example to show you, or if you like, up to here. What is the area under the delta U curve? Is 1 plus 2, 3. You see my U curve? Up to here is 3. So the U curve is area under the delta U curve. All right, so this is area. Which means it's output of integration. All right, is this one. Which means this is the input, this is the output. The output is the area of the input. And so there's integral control. This output is the integration of the input. All right, so the maths will be like that. So that is the understanding. The maths will be like that. You take Z transform, you get this. This one Z transform, you get this. This one Z transform, you get this. So you rewrite, you will then get this. Okay, this, if you remember, is the transfer function of integration. All right, whatever input goes through this transfer function, the output is, this is integral control. Okay, so let's go through a few more detail. Now, so how to include integration into the plan? It is, the integration is included into the plan. It is not included into the controller, all right? So that's why it is called augmented state space model of the plan, all right? The controller, so to speak, the MPC controller don't have integration. Integration happens in the plan model, all right? So we augment means enlarge, make it bigger, all right? English word for augment means, so which means by right, the plan is smaller. The plan is smaller. This A, B, and C are smaller matrices and vectors. Because we put in integration, so it becomes bigger in the sense that the dimension of A, B, C will be increased by 1. Okay, so we take a look. We first of all define delta. Delta is always the change. So delta xp is xp minus xp plus 1. So if you do that, then using 2.1, which means this is simple. Look at this equation. So it's xp. All right, then k plus 1 is this xp. So if xpk, then this must be xpk minus 1, that kind of thing. So you do that, and then you subtract the two things, you will get this. All right, nothing complicated algebra. So you get this. Then since we define delta as the change, so this must be delta. All right, this must be delta. And then also this must be delta over here. Okay. Then you use 2.2, you go and find the delta also, yk plus 1 minus yk. So you stick this in, you use 2.2, you just use 2.2, you put a yk plus 1, you will get xpk plus 1. Then you go and subtract, you will then get this. All right, then this again is the delta. Okay, then you just use this, rewrite yk plus 1, you will get this. It's just algebra. Now then, once you get that, you form the state space. How you form the state space? Define the states as this one, which means define the, you draw a vector, this is the vector. All right. Delta xpk plus 1 and yk is the vector. It's the state. So if you write this as the state, so you write it down, this is the state. And this, since it's k plus 1, is standard state space. If this is the state, then you got A times the state. Here is the k plus 1 version of the state. This is the k version of the state. So you see this is k plus 1, this is k, so this is standard. All right, once you define the state like that, these two, xk plus 1 and xk is defined, and you write it down. Okay, this is what I will do. Once I define that, I write it down. Then you go and look see all the previous equation and fill up the matrix A, B, and C. So, which means how you fill up the matrix A, you go and look at the equation, you see all. Delta xpk plus 1 is AP times delta xp plus BP plus delta U. You go and look. Oh, there is this one. So I need to get this equation. So I get this equation. So I put it here. So now I can connect this with this and this. So at least I got the one element of A, one element of B. All right. Then after that, I see, oh, how I get yk plus 1. So you go back and see again, yk plus 1. Ah, this one. So I must get this got to do with CPAP times delta XP. You see CPAP times delta XP. Ah, so I write it down here. Okay, plus Y. So 8 here. Okay, so I put a 1 here. So this times this must be equals to this. Then BP delta U. So BP delta U. So this second row will give me this. So, okay, so it's look see. Make sure you look at the algebra from all the previous equation and fill up the A, B, and C matrix. It's standard. The trick is, first of all, identify the state. So once you identify the state, this must be the k plus 1 version. This must be the k version. Then you got basically A, B, C to fill up. Then go and look. That's what I do. I look. Then I fill them up. Then I know that written inside here, 2.5 and 2.6 contains all my previous equations. All right, it's now rewritten in 2.5, 2.6. Nothing new in 2.5, 2.6, except that it is now organized into ABC, so to speak. All right, so this is standard undergraduate state space control. Now, we look at an example. So, maybe now I draw for you so that things maybe will be a bit clearer now. Okay, with this, what is happening now would be that your real plant, all right, your real plant, let's say this is your real plant. Was given by this model, AP, BP, and CP. Okay, so remember this is described by AP, VP, and CP. Okay, and the input to the real plant, like I said before, is U, not delta U, but U. The output of the real plant is Y. Then before that, remember how is delta U related to U? Input to here is delta U. And this transfer function is this one. Okay? Delta U times this is equals to U. So it's 1 over 1 minus Z minus 1. All right, and this is integration, which means this is area under the delta U curve. And then this one is what we call the augmented plant. And the matrices are A, B, and C. All right, with this one. And the MPC controller will calculate delta U. All right, so it will be like that. Okay, then the MPC controller calculate delta U. So maybe I put delta U outside. All right, input to the ABC, the augmented plant. The output of the augmented plant is Y. So we say this augmented plant, this is the real plant. So because the real plant is now enlarged, because we added an integral action here. There is no integral action in the algorithm, but the integral action is placed inside here. Okay, so this is standard actually undergraduate control, but I just want to make sure it's very clear and so on, so that later on you will have. Okay, let's continue. So look at a simple example, put some numbers and so on so that you know. So let's say it's a first order process, which means the plant has only one state, not two state, one state, first order. So all these are scalar. So find the transfer function. So now find transfer function. You take Z transform, this one will give you this. All right, this will give you this. This will give you this. Then this will give you this. And then this will give you this. All right, then you take Y over X. Sorry, Y over U. You go and work out the algebra Y over U, you will get this. So this is the transfer function relating the real power with the output. Okay, because it's U, not delta U, it's real one. Not the calculated one. So real. All right, then find the augmented transfer function, which means now is Y over delta U. Delta U is not the real power, it is the calculated power by the MPC. that haven't gone through integration yet. It's not the real number, that wattage that you send to the plant. Okay, to do that, you then look at equation 2.5, which is like that. All right, the formula are given. So you have to go and take a look. What is A, B, and C? Basically force you to go and look. This one, 2.5, this one. So you go and put AP, CP, or you put it inside. So you will get this. And then the augmented states is like that. So now with that, you use this formula. Now, this is a standard formula to convert state space to transfer function. So, which means what? When you have this, convert this to a transfer function, y over delta uk, which is inside here. So you use this formula. You put C, which means you put C here. You put B here. You put A here. All right, you go and do, you will get this. Then you rewrite a little bit, you get this. You bring delta U over, you get this. Then you can see all. Okay, so now this is clear. Make sure you see that things are clear. This is MPC calculated. All right, power. This you see before. You're going to look before. This delta U times this will be big U. So delta U times this is big U. All right, this is real power. All right, then this is integration. Then this is the real, you see, the real transfer function of the real plant. This is transfer function of real plant. And then if I do some more from here to here is the transfer function of the augmented plant. Okay, so all the pieces, make sure you know what is what, then you don't get confused. Okay, so now we finish with the plant. Now we can go on to the control, the MPC control derivation. Now, the states of the plant is xk plus 1 equal to ax plus b delta u. All right, 2.5, which means now we are dealing with the 2.5. 2.5 is here. Xk plus 1 a xk b delta u. So it's like that. So if this is xk plus 1, xk plus 2 will just be from k become k plus 1, from uk become uk plus 1. All right. So it's the same equation except k plus 1 become k plus 2. Then it's a standard trick that you say, hey, this is xk plus 1, which is this equation. So I can replace this by this whole thing. So you put this whole thing inside here. If you do that, you will get this. Then you write down xk plus 3. So since you got xk plus 1, from here, you sure can get xk plus 3, which means k plus 1 become k plus 3, you just add 2. This one is add 2, you just get k plus 2, so you get here. Then you say, hey, this one, xk plus 2 is this one or this one. So you take this whole thing and substitute inside here. If you do that, you will just get this equation. So if you are patient enough, then you can get NP. You do dot 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 until NP, you will see this pattern. Okay. Then after that, once you get this pattern, then you go and look at 2.6, which is the output Y. Oh, 2.6 is nothing but Y is C plus, no, Y is C times X. So you will say YK plus 1 is C times XK plus 1. Y, which basically is like that. All right. Then you see, hey, what is xk plus 1? You look, is this one. So you put inside here, you will get this. Then what is xk plus 2? Which is this one. So you C multiplied by this one. You will get this. All right. So this, needless to say, is C xk plus 3. So you got xk plus 3. You got this one. So you put inside here, you will get this. All right, same for this one. So needless to say, this will be CXK plus NP. So you got this pattern here. All right, you put it inside here, you will get this. Okay, so now you got your Y, your output, all like that. Then now you go and write into matrix form. All right, this matrix, you cannot write like that. So you write into the matrix form. So what you do is you say this is the Y matrix. You take this. Then you say, I write this and call it the Y matrix. Then X, oh, that's easy. All this, okay. All this U, which means delta U. And so on. All right, you call it this. All right, you got delta UK plus 1, delta UK plus 2, dot, 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 all the way until you finish up to here, you put it inside here. Then the XK is easy. XK is this one. Okay, and you put it inside here. It's just XK. Then in front of XK have to be multiplied by all these things, so you put it into a vector, which is this one. Okay, so all the CAs, you call it F. Then whatever left over, you call it phi. Okay, so I write down neatly for you here. Basically, it's nothing. All this, you rewrite everything inside. Capital F, capital phi, capital Y, capital delta U. All right, from here, you just go and organize here. I write it down for you nicely. What is this? Okay, now is 6:45. Go for a 15 minutes break. Come back at 7. I will continue talking at 7. Okay, so now we basically got Y. All right, the output in terms of the input delta U and the states. So now we go to the control, which is called optimization. Now we are trying to minimize an objective function. Basically is J. It's written like that. If you are not comfortable with matrices and vectors, then just understand it using scalar, which means J is equals to half. If all these are scalar, then you don't have such thing as transpose, then all you have is nothing but RS, which is the set point, minus Y square plus delta, this one delta. All right, this one delta U. There's no such thing as transpose for scalar, so it's plus delta U square times R bar. Okay. So now you can see what is this trying to do is you try to find the smallest J. RS is the set point. R bar is a weight, that a design parameter that you choose. So now how to make sense of this? If you choose R bar to be very small, let's say 0, then this clearly makes sense. You want to find the smallest J, which means it's the smallest RS minus Y. This is a set point. This is the output. You want the smallest J means you want Y to be as close to RS as possible. The best is 0. 0 means your output Y is equal to the set point. All right. So, which means assuming that your Y is at 0 when you first start, then you put a set point of 1. Then when you first start, this will be 1 minus 0 is 1. So your controller will quickly try to make Y from 0 quickly go to 1. Maybe after first sample is 0 or 0 sample is 0, then first sample is 0.5, second sample is 0.9, third sample is 1. Then after fourth sample is 1, fifth sample is 1. So this square is as small as possible. Okay, so then the next thing is this is control power calculated by your MPC. You on one hand, you also want to make sure you don't want to use infinite power. Is ridiculous. Doesn't mean yes, you want Y to be as close to RS as possible, but you also want to minimize power usage. So you balance it. All right. So you don't set R bar equals to 0. You set R bar equals to something. So that while minimizing J, you also consider how much power is being used, calculated by the controller. So R is a tuning parameter. So which means if R is huge, then you're saying, oh, I want to minimize J, means I want to minimize delta U. I don't care about performance. This one, Y can go to RS slowly, but I must make sure that this is small because R is large. This component is large. All right, J is largely made up of this. All right, which means to you, power is more important than performance. All right, if R is 0, then performance is more important than power, energy. Okay, so R is a design parameter, and typically R is the identity matrix multiplied by RW is a number that you choose. Okay, so this one will go inside here. So now I say we want to make J as small as possible. So Y, we stick in Y from here. So we got Y. So we stick in here or stick in here. If you stick in here, then you multiply, you write things out, it will look like that. And then we say we want to find the minimum J. So we will find the minimum J, dj, d delta u is standard, dy dx, will find the minimum Y at where is the X that gives the minimum Y. So you find what is the delta U that give you the minimum J. All right, so you go and differentiate this. Now, it is obvious since the last part doesn't contains U, this one doesn't contains U, so you can forget about it. Because you are differentiating J with respect to U, so it's the same as writing J like that and differentiating J with respect to U. Again, if you are not comfortable with matrix, you just understand this using scalar, you will then write J is equals to half delta U square in all right. If you differentiate dj, du, this square comes to the front, so you will just get this. All right. You differentiate dj, this, just remember all these are scalar, so there's no such thing as transpose or what, although it's written here, because in general it is matrices and vectors. But if you are not comfortable with it, then I suggest you just look at it as scalar and see that, hey, you differentiate. If this is a scalar, dj, d delta u, this one will be gone. You're left with this. See, hey, left with this. It will work. All right. So you will get this. Then after that, secondary school say, okay, you want to find the minimum J, you will equate this to 0. So you will equate this to 0. Like I say, then this is equate to 0. You want to find delta U, then you bring this over, all this to this side. You will then get this. All right, which means bring this to this side, then this one divide by it. So delta U will be equal to this. All right, matrices divide means inverse. If it is not, you will basically get delta U is equals to phi transpose RS minus F. All right, this will be the scalar version of this. Okay. Okay, so now once you get this, this would be the power that the MPC will calculate to minimize J, and J is really this. All right, depends on, you want to minimize and make sure the output as close to the set point as possible, and also you take into consideration the how much power you use. That depends on what you choose for R bar. If you choose R bar equals to 0, which means I don't care power, I just want performance. Like I design a sports car, my power, you don't care. You must go as fast as possible. But you want an economical car, then you choose an R bar large. So performance is not so important. You know, rural economy is important. So your R bar must be big. All right. So okay. So that is done up to here. Now, then so it's just algebra, nothing big deal. Here, typically the RS is the set point. They will break it up into RS bar and RK. So this one is just broken up to here. It's nothing much. It's for convenience of, it's just for convenience of algebra. All right, RS are just all ones. Then R would be your set point. All right, normally your set point, you just multiply by all ones. That will be this required vector for RS. Okay, now, then the whole idea of model predictive control would be what we call receding horizon control. Now, this one makes sense in practice. We do it all the time, but let me just explain things carefully. It is something that we do all the time. Now, assuming that next Friday is this computer control exam. So next Friday. So what will we do? So we have now we have to plan to study for it. So we have Saturday, Sunday, Monday, Tuesday, Wednesday, Thursday. Then Friday you will go for exam ready. So you will then plan. Then you think, okay, you have Xiangchen's part, you have my part. So you think, okay, Xiangchen's part is very easy. So you think, okay, tomorrow, Saturday, I will study Xiangchen part. Sunday, I'll study Xiangchen part. Then finish already, because my part is very difficult. So you reserve Monday, Tuesday, Wednesday, and Thursday. So this is my name, WK. So this is your plan. Just like model predictive control, you will plan. All right. This is planned, but when you execute, you can only execute one day at a time. So tomorrow you wake up, you study. You will execute, you study Xiangchen part. Then study finish already, tomorrow night, Saturday night, then you think, wow, he teach so badly, I don't even understand what he say. I must replan. So, okay, so which means you just execute one part, You see, I'm teaching you the receding horizon, which is always what we do. You execute one part, you can really execute tomorrow at Saturday. You just execute Saturday. He teach so badly, you don't understand what he say. So you have to cannot. You have to replan. You say, okay, Sunday I have to study Xiangchen part, Monday also I have to study Xiangchen part, then Tuesday then you study my part, Wednesday study my part, Thursday study my part. All right. So actually at this point today you plan, tomorrow you just execute the first part. After tomorrow you have to plan, then Sunday of course you will just execute the first part. So you execute, you go and study Xiangchen part. Then, okay, you study already, Sunday night, wow, you say, cannot understand. You give up on this part. So your plan now is, you only study my part, okay? So on Sunday night, you plan like that. So on Monday, so you study my part. All right, so the whole idea is that as far as the algorithm is concerned, the model predictive control is concerned, you plan all the way. But you every time you execute only, you take out the first power that you have calculated, you send it to the plant. Then at the next sample, you plan all the way for as long as you choose to. Then you just take out the first power for that, the next sampling instant, you just send that power. So every time you keep on doing this way. So that's quite normal. You can see this, what we do every day. We'll plan, and then we can only do one thing at a time. So tomorrow we do what we have planned. After tomorrow night, then we have to look at what we have. Then we replan again. Then, Sunday night we plan again. Then Monday can only do what we can do on Monday. Then Monday night plan again, So that is receding horizon. That is the whole idea. So which means now we just look. The control signal actually here contains, if you look, all the action that all the power that you plan to send out. Delta U, it was defined here. You see, I draw for you here. Delta UK plus 1, delta UK plus 2, and so on, which means tomorrow night, Sunday night, Monday night, Tuesday night, all the nights for as much as you plan. So delta U actually contains all the power that you have planned to use. But when you execute, you only will execute the first element, which means tomorrow only. All right. So that's why in front of this, which is this one, here, you put a vector that has 1 here and the 0 all the way. This effect will be when you multiply by this, you will only take out the first delta U. All right. Delta UK will only be taken out here. Delta UK plus 1 will be multiplied by 0, will be gone. Okay. Here contains all. It is planned. It is there. But you only take out the first unit, the first element. All right. And use the first element. Okay. So that is done. Then, so just to do the algebra, so you normally will multiply this all the way out. Okay, so you multiply this all out, and then you call it KR. Okay, KR is here. This is your set point, so it's here. Again, then you multiply all the way out, then you call it MP. All right, XK is here. Everything go and multiply out. Whoever multiply by XK, you call it KMPC. Basically, I write it down properly for you. It's nothing but this 100 times this thing, inverse times this, then you just call it KMPC. Okay. So I just tell you, note that KR is the first element of this and KMPC is the first row of this. Basically, they are the first row or the first element. The rest of the row and the rest of the element is all thrown away. Okay. So now you got this delta U is this, then you originally the plan is what, 2.5. Where's 2.5? That was the original plan. 2.5. Then here. So you replace, now you got a formula for delta U already. So you replace delta U with that, what, KR times R plus KNPC times XK. So you throw it inside here. If you do that, okay, you do that, you get this. You do a bit more algebra, you get this. Okay, then after that, then the standard thing, you go and do write this as a transfer function. Again, if you this one, you write a transfer function, all right, because you 2.6 is really nothing but yk equals to cxk. All right, so you got yk become yz equals to cxz. Then this one is z into xz. Then all this is xz. Then this is rz. All right, you have this. You have plus bkr. So you do all this algebra. You then get your yz over your rz. So this will be your transfer function. If you are not comfortable with matrices, you will find that you treat all this as scalar, you will get yz over rz is equals to scalar. You will see that b kr is over z minus a minus b k MPC. Okay, so you want to find the poles. What you do is in transfer function scalar, you just equate this to 0 because in general this is not scalar, it's a matrix. So you just take the determinant equal to 0. If it's transfer function, then you just equals to 0. If it's scalar, it just equals to 0. See, if it's matrix, you just take the determinant. Okay. I can't spend time on this already. This is undergraduate stuff. Okay. So now I draw the whole picture for you. It is here. The whole block diagram that organizes things for you in picture form is here. Okay, let's do one piece by one piece first. When we first do the BP here, this is the real plant. You see, output of the real plant, input of the real plant is UK. So this is the real power. So this is the out plant output. All right, so that's clear enough. This is a real plant. So real plant is real plant. And this is described by AP, BP, and CP. Okay, so this is the real plant. Then the augmented plant is here. The augmented plant is here. You see, this become part of the augmented plant. And you will write the ABC of this. You will be, I have given you a formula to write the model, state space model. You have to use A, B, and C. And how this is related to AP, BP, CP, I already gave you the formulas. Then now, you can see that here, this part here is the MPC. All right. So this is the MPC. You need to stick in a KMPC to multiply by X. All right. Minus here plus a KR that is from the MPC calculation to multiply by the set point. All right. Then it will compute this MPC calculated power. Okay, so this is the overall picture of what we have up to now. So let's look at one numerical example to, put all the things together before we move on. So a simple tank example, the real input would be U. So this is, let's say in 1 second, how much the volume of chemical that flows in. In 1 second, the volume of chemical that flows out. So in 1 second, the volume will, let's say, just to make things easy, the volume will change by how much depends on how much flow in minus how much flow out. So you write down the equation. H is the height here, height times the cross-sectional area, which is this one. All right, cross-sectional area must be equals to volume. And since we say in 1 second, so I'll put a H dot here, which means A will not change. Cross-sectional area is the same. So in 1 second, what is the change in volume, or what is the, or H dot, which means the speed, in 1 second, how much H change. So I put a H dot here multiplied by A. So it's equals to, in 1 second, how much Q come in? My how much U come in minus how much Q go out. All right, U come in how much minus U go out how much will be in 1 second the change in volume. So you get this equation here. It's standard that the how much flow out depends on the pressure, which depends on the height here. So it's proportional to the height. So Q is replaced by H divided by R. R is a proportionality constant. Okay, the bigger the H, the bigger the Q. So you do like that. So this would be the starting equation. Very simple one. So now you rewrite this and let XP be H, which means the state of the plant is the height of the chemical in this tank. So you rewrite this, you replace H by X, you H dot become XP dot, H becomes XP, then U is this U, then you will get here. This will then bring you here. The output is the height, which is H or XP. Then you discretize this using the forward difference, which means you see this forward difference. I can't teach that anymore. This is a slope. You just use the next state minus the previous state divided by the difference in time. All right. So in this simple question, H is 1, which means 1 second. So H is gone. This is 1. So life is easy. This is 1. All right, this is 1. So if that's the case, then you rewrite everything, you will get this. Finally. This is the state space that I've been discussing, since 6 o'clock for the plant, the real plant. This is the real input. All right, AP, BP, C, all the numbers are here, which comes from here. All right, if you stick that in here, you will get all this. So there's nothing. So this is the real plant. Then standard, you will now, then is specified NP is 3, NC is 2. All right, the set point is basically 1. Before you start K less than 0 is 0. So now the weight RW is 0.01. So find delta U. And big U, small u, no delta UY. Just is basically an example to make you put the numbers into all the previous equation and get some numbers out so that at least you know how the equations are being manipulated. Okay, so 2.5 and 2.6 will give this. 2.5, 2.6, basically, this is the real plant. 2.5, 2.6 convert the real plant to the augmented plant. So from AP, BP, CP, 2.5, 2.6 give you A, B, and C. So you have to go back and put the number into the equation and make sure you get this 0.8 here, 0.8 here, 0.1, 0.1, 0.1, 0. I won't discuss. There's nothing to discuss. Just go inside, put the number inside the formula, and you will get these numbers. Okay. Then after that, also, there is nothing much to discuss. Look at 17, 18, 21, 26. With all these numbers here, you will then get this. All right. So You see, now with this, then 25 will then give you delta U, big delta U, and small delta U. Okay, so you go and look at 25. 25 is when? Okay, you go and stick in, you already got 5, you got all this R, bar, RS, F, XK, you go and calculate 25. If you calculate 25, you will get the big delta U for K equals to 0. So, like I said before, this is what you plan. You plan for this U and this U. All right. So you plan for 2U because you choose the NC as 2. If you choose NC as 3, then you plan 3U, which means you plan 3 days ahead. If you choose NC as 4, you plan 4 days ahead. So you have 2. Then like I say before, you can only do the first one. So your calculated power, you take the first one. Okay? This is the calculated power. This is the real power you are going to send to the tank now. Or the real or power or the real volume of chemical you are going to throw into the tank now. Is the previous chemical, the previous U, which by definition, the question say previously before you switch on, it is 0. So this is 0 plus this one, this is here. So you will get this. So the real power that you are on for K equal to 0, or the real volume at K equal to 0, the 0th second you put into the tank is 4.98. Okay, so if you put 4.98 inside, then 2.5 will give you this, and 2.6 will give you this. So now you got a power, 2.5 will give you this, and 2.6 will give you this. You have to go and do. Then now you go back and do K equals to 1. So the next second, or the first second, this is the 0th second. The first second, again, this one will give you this. So you really must go and put some phi and all these numbers inside here to get this. And then after that, like I say before, you only execute the first one. So you take this out. This is what you will do. You basically throw away this. You throw away. Never use. Throw away means it's calculated, but you will never use. Okay? So then you have to send the real power, which is defined as the previous power. So you look at the previous power, is this one. So you must take this, which is this one, so you put it here. This is this one, so you put it here. So you go and add them up, you will get this. Then this will be the real part, the real volume that you will put into the tank. All right, then once you have this, then you go and calculate x2 and y2, which is use 2.5 and 2.6. So you get this. So the k equals to 2. I think I won't explain anymore. It's just the same as before. All right, so all the numbers are here. So now part C. Actually, this whole example, if there's nothing except that I force you to start putting numbers into equations, then so that at least you know the equation work. Find KC and KMPC. So nothing much. You just have to go and use this and this. Then you will get these two numbers. All right. Then 29 is the formula for this. It says that KR times R minus KMPC times X. So R, for this example, is always very simple. It is a set point of 1, so this is always 1. And then when we first started, the state is 0, was given in the question. So now you see how you get this. KR was this, so you put this inside here. This is 0, that's why the first delta U is this. Then you should compare. 4.98. Previously, you calculated differently. It also say 4.98. Okay, different way of, or different formulas, different equation to calculate the same thing. Okay, so I make sure you link things up for yourself. Then, like before, this is 0. So the first real power is the previous real power, which is 0 plus the MPC calculated power. So is this. So you get this. Then you compare, it's the same. Then, what is x1? You use 33, you calculate, you get this. Then you compare with, is this the same as the previous x1? 4.98. Then 4.98, or it's the same. All right, previously you used 2.5 to calculate x. Now you use 2.33 to calculate x. Though they look different, but actually they are all derived from each other. You must get the same answer. So make sure you connect things up. If not, you'll be all over the place. Then you don't know what is happening. So it is a necessary exercise. Okay, then after that, delta 1 is K times R1 minus MPC times X1. So R1 is again 1. The set point is Z. X1 is this. So you have to stick that inside here. All right. Take this, multiply by this. It will give you this answer here. Then U1 is the previous U, which is this one. Stick that inside here. Okay, then this one, stick that inside here. You find U1 is 4.52. You must compare with here. 4.52. Same. Calculated differently, but same. Okay, so you go on and make sure you can connect things up. E asks you to now find the closed loop transfer function. So 34. So you go to 34. You go to 34, which is this, the closed loop transfer function. You stick in ABC, everything, you will find this 34. All right, then you work out, you will get this. Then find YK from the closed loop transfer function. So since the closed loop transfer function is like that, you multiply things out, you will get this. All right, from Z, you get, if from Z, I can't teach already. From Z, you will get K. Z minus 1, you get K minus 1. Z minus 2, you get K minus 2. So, okay. So from here, you get, from Z, you will get your K. So you get here. So y equal to 0 is 0. It is given in the question. Then y equals to 1. Is this one. How you get this one is because when y is 1, this is 1. So you get here. I think you get here. When k is 1, y0 is 0. Y minus 1 is also 0. So this is 1. So you get this. All right. Then you got to go back and check y1. Previously, you got y1. Is it 4.49? y1 previously we got that 0.49 is correct. Because we have so many equations, so now forced to connect things up. So from here, you get y2, y3. So you go back and check all these are the same number as before. All right, all the y were given to you before, calculated using different equation. Okay, so this example is make sure you put numbers into equation, and there are many confusing equations. Actually, they are the same. They give you the same answer. You must convince yourself of that. Tuning. So in practice, when you have a model predictive control, you have to decide on 3 things: NP, NC, and R. So in practice, in the industry, what you do is, starting point, you choose NC as 1. All right. And then NP, you choose, if you do digital control, normally the norm is the open loop rise time, you must sample about 10 times to 20 times. So you typically, you do the open loop rise time, which is between 4 to 15. So NP is typically 4 to 15. You can just choose 10. That is the starting point. All right. At least now you know you don't go and choose NP as 1,500, you know. So you just choose NP as 10. You have to do simulation to that's why it's called tuning. Tuning is like the radio like that. There's a knob. You turn left, turn right, turn left, turn right. You listen. Okay, this is the correct sound, that kind of thing. All right, so the starting point, NC is 1, NP is the rise time. Then there is this R, which is the weight that I told you before. So you go and see, if you want to do a sports car, then you put R equals to 0. So all you're making this performance, your Y, to be equals to your R as close as possible. All right. And then you don't care about delta U, because R is multiplied by delta U. If you want to build an economical car, then you choose a big R. Then this one has less influence, because delta U would have more and more influence with big R. Then after that, you have to do simulation on the computer. Then you load, and then you decide on the final number. Okay, so that will be the practical way of designing the model predictive control. Now, it's the last thing. You see, in model predictive control, we require 2 things to do the calculation. You look at the formula. We need to know X. R is your set point. So you set by U. If it is your oven, you want 90 degrees Celsius for your oven, you put 90 here. XP is the state. All right. Sometimes you don't have the state. You don't have the state. So if you don't have the state, then you will have to estimate the state. All right. So it's like in manufacturing, sometimes, especially let's say in semiconductor manufacturing, the wafer, the wafer, you inside the clean room, everything is very clean one. They won't nobody no, you cannot use a temperature sensor go and measure the temperature of the wafer. You will spoil it, you will dirty the whole thing, everything will be gone. All right, the clean room. But you need to know the temperature of the wafer because you need to control the chemical reaction that is going on in the on top of the wafer. So you have to and the state is the temperature. So from whatever output that you manage to measure, maybe you measure the temperature of very far away from the wafer. Then after that, then you measure the airflow, then you measure all sorts of things. Then from there, you have to go and estimate the state, which is the temperature of the wafer. All right, so you may not be able to get X, you get Y. Y could be temperature of the box, temperature of the oven, but X is the temperature of the wafer. Okay, so you need it. So you go and estimate it from Y. So one way, simple way I already teach you before is to use Kalman filter. Kalman filter was hot. It's like that. This is Kalman filter equation 155. You go and look. We use 5, whatever we can measure to get an estimate of X, the state. All right, that was Kalman filter. You remember Kalman filter? That time when I teach that time, I keep on saying, this equation and this equation, this is the X is the real temperature inside your body. It's like the wafer. This is Y is the temperature that you use the gun to measure your head. It's the same as the wafer. You can only measure the oven. You cannot measure the wafer. You dirty the wafer. So the oven temperature. From there, you have to estimate to get X, the wafer temperature, just like I want to know the temperature inside your body. It's not practical. I take a thermometer, whole day stick inside your mouth. All right, it's the same for manufacturing. So from there, you measure Y, you get Kalman filter to get your X. So we will use Kalman filter 1.55. Now, bear with me for 5 more minutes, pay attention, then I finish. So we will use Kalman filter 1.55. Look, 1.55 will estimate the state xk plus 1. The previous xk was assumed to be estimated previous sample. Yk obviously is the temperature that you manage to measure whatever the oven temperature or your forehead temperature, but you cannot measure inside your body, just like you cannot measure the temperature of your wafer. All right, you use this equation to estimate the wafer temperature. Then every time your model predictive control that requires X in the formula, you just use X hat. That's all. All right. Up to now, I just teach, we always use X in all your calculation. So you don't have X, so you just use X hat. Every time you see an X, you replace it with X hat, finish. All right, that is state estimation. A few things to say. Kalman filter two things. This is the Kalman filter from 1.55. I wrote it as K. Here, I rename it as KOB because we are using it as what we call an observer. All right. Here, the name is called an observer when you use it to, with respect to a controller, you call it an observer. It's just a name. All right. K is K. So K is equals to KOB. Then the next thing is in Kalman filter, you remember we always have xk/k or xk+1/k. So here don't have to be so troublesome because we only use 1.55. And 1.55 is forever. If you look at 1.55, it's forever xk+1/k. This is k/k-1. But we will never use xk/k. So forget about the slash. So we just put k+1 and k. Because we will never use the k+1/k+1. It will forever be k+1/k. This is k/k-1. As if we just use the simple 1.55 for Kalman filter, we are not using the Kalman filter for 6 equations. We are not using the other 5 equations. We are only using 1 equation. So don't need to be so complicated because this kk and k+1k appear in the other 5 equations. All right, let's forget about them. If not, it's very confusing. So it will be simplified to this. Next, the Kalman filter tutorial questions that we did, you can see that Kalman filter gain will actually reach steady state, which means when you use a Kalman filter, your K actually change. Your P in Kalman filter also change. Your KF also change. But that's a steady state. So after a while, all the P, all the K, all the KF, everything will reach a constant. So as far as we are concerned, when we use it as an observer for model predictive control, we will use the steady state value. All right, which means here our K is the constant obtained from Kalman filter. Technically speaking, after the Kalman filter reach a steady state. In other words, simply say K is a constant here. It's not changing. In Kalman filter, it is changing. But Kalman filter change. After a while, also will remain constant. We are using that part when it becomes a constant. The last thing to say is make a distinction. As far as the way I teach you, in model predictive control, the plant got no noise one. All right, you see all my plant for model predictive control, the ABC got no W and V. Whether the real plant or the augmented plant is such that there is no noise here, no noise here, not like Kalman filter. Okay, we keep it as that. You learn this version first, don't complicate things. It's like that. Kalman filter here got a W and a V. And this, the variance is R1 and R2. And we saw in Kalman filter, the model is like that. All right, the model Kalman filter, we started the model is like that. And then the variance of this, I call it R1. The variance of this, I call it R2. And then you start to run this. All this K, which is here, this one, I changed to KOB already. As when I use model predictive control, this one become KOB. I use 155 for MPC. What KOB will finally be depends on R1 and R2 as far as the maths is concerned. And I spend a lot of time to tell you, R2 tells you how much the noise you expect from your measurement. If you have a very expensive, temperature gun, then R2 would be very small. If R2 is very small, then Kalman filter will believe the expensive temperature gun measurement. All right, if you have a lousy gun, then this one will be very big. Then relative to this, your Kalman filter will believe this equation 50 more. So all those were taught previously. So R1 and R2 will be used to design this one. All right. So based on your wafer, you have your wafer. If you use a very expensive, oven with very super expensive temperature sensor, then you will believe this more. All right, if yours is a cheap oven, then your R2, you go and put a bigger one, bigger number. So you'll believe this more. So you will end up with a different KOB. So that would be how you design this we call observer for your model predictive control. Okay, I think I'll stop here tonight. That's enough for you to think. I see you next week.